Welcome back to AI.Code.Cast. Today, we're going to be tackling a pretty interesting problem. It's a classic coding problem. You might come across it in a technical interview. It pops up in the real world, too. Dealing with data structures. We're talking about finding the intersection point of two singly linked lists.
Yeah.
It sounds a little intimidating. It's like, imagine you have like two roads merging into one.
Right.
That's kind of what we're dealing with here. But instead of cars, we have these nodes connected by pointers.
It's a really good way to think about it. It's a fundamental problem, really tests your understanding of how linked lists work and how to work with them efficiently. And it has applications in all sorts of areas, like say you're trying to detect plagiarism.
Wow.
Or like if you're building out a family tree and trying to find common ancestors, it's the same kind of problem.
So it's not just a theoretical exercise. There's real-world stuff going on here.
Exactly.
Okay, so to make this a little more concrete for our listeners,
Yeah.
let's say we have two linked lists, right? Each of them is a chain of these nodes.
Yeah.
And at some point they merge, they have this common tail.
Yep.
And our goal is to write some code that can pinpoint exactly where that merging happens. Where do we even begin with something like this?
Well, I think it always helps to start with the simplest approach. Even if it's not the most efficient, we call that the brute force method.
Okay, brute force. So if I were to approach this like I was some kind of detective,
Right.
I'd probably take each suspect from the first list and compare them to every suspect on the second list.
Yeah.
Is that kind of what we're doing here?
That's exactly what we're doing. In the brute force method, we go through every single node in the first list.
Okay.
And for each one, we check if it's in the second list.
So we're talking about nested loops here.
Nested loops, you got it.
Okay. So one loop going through the first list, and inside that, another loop checking the second list.
Yep. And this is where it gets a little tricky. We're not just comparing the data in the nodes, right?
Okay.
We're looking for the actual same node in memory.
Okay. So two nodes could have the same data, but they're different entities in memory.
Exactly.
We're not just matching data, we're matching the physical location where these lists come together.
Exactly. We're comparing memory addresses. And, the brute force method, it's easy to understand, but it's got a big downside. It can be really slow.
I can imagine.
And
Especially if we had these giant lists.
yeah, especially with the large lists.
We'd be comparing nodes forever.
Yeah. And that's what we call time complexity, how the time it takes scales with the input. And for this, it's O of n times m, where n is the length of the first list and m is the length of the second list.
Right.
So if both lists have 1,000 nodes, you're looking at 1,000,000 comparisons.
So brute force, it's like that reliable friend who always takes the scenic route. We need something a little faster. What else do we have in our coding toolbox?
Well, to speed things up, we could use a hash table.
Oh, hash table.
It's like, imagine a really, really organized filing system where you can store information and retrieve it really, really quickly.
So we're moving from brute force, checking every single suspect,
Yeah.
to something a little more targeted.
Right.
How would we use a hash table for this?
Okay, here's the strategy. You go through the second link list, and you store each node's memory address in the hash table.
Okay.
And remember, we're storing the address, not just the data, because we're looking for that specific node.
It's like creating a catalog of all the nodes in the second list, with each entry pointing right to where it lives in memory.
Exactly.
Okay, then what?
Then we go through the first list, and for every single node, we check, is its memory address in our hash table?
Okay.
If it is, boom, we've found the intersection.
Oh, it's like using a metal detector. Instead of digging up the whole field, we only check the spots where the treasure might be, that intersection node. This has got to be way faster than brute force.
Yeah, much faster. Searching in a hash table is on average O1 time complexity, which is super fast. So, building the hash table initially takes m time, where m is the length of the second list, and then searching through the first list is OM.
So OM plus ON, much better than the brute force ON times M. We've saved a lot of time. But I have a feeling there's a trade-off here. We're using extra memory for this hash table, aren't we?
You're right. That's the classic trade-off. The
Yeah.
space complexity, how much extra memory we're using, becomes OM because we have to store all those nodes from the second list in our hash table.
It's always a balance, isn't it? Speed versus memory. If we've got memory to spare, hash table looks like a winner.
Yeah.
But what if we're working with limited memory? Is there a way to get the best of both good speed and minimal memory?
There is. And that brings us to the most, kind of the cleverest and most efficient solution, the two-pointer approach.
Oh, this is where things get interesting.
Yeah.
I'm ready to hear all about this two-pointer strategy.
All right, let's dive in. So the two-pointer approach. This one really throws people off sometimes.
Yeah, I can imagine.
But once you see it, it's like, oh, that's pretty neat.
Okay, I'm all ears. How do we even start using two-pointers for this? It seems like we're just making things more complicated.
Okay, so imagine you have like two runners on a circular track, right?
Yeah.
Even if they start at different points and run at different speeds, eventually they're going to cross paths, right?
Right, yeah.
So think of our pointers like those runners and that merging point in our linked lists, like the spot on the track where they meet.
Ah, okay. I see where you're going with this.
Yeah.
So we're going to make our pointers kind of run through these lists
Yeah.
in a way that forces them to meet at the intersection if it's there.
Yeah, exactly. If the intersection exists, we're going to make them hit it.
Okay, so how do we actually do that? Where do we start these pointers and how do they move?
Okay, so we start with a pointer at the head of each list. We'll call them pointer A and pointer B.
Okay.
And we just start moving them through their respective lists.
So pointer A goes through list A, pointer B goes through list B. What happens when they reach the end of their lists?
That's where the trick comes in. When a pointer reaches the end, we make it jump to the head of the other list.
Whoa, wait a minute, hold on. It's like our runners teleport across the track.
Yeah.
So pointer A finishes list A, it jumps over to the start of list B and vice versa.
Exactly. And they just keep going one step at a time until one of two things happens. Either they meet at the same node, boom, that's our intersection,
Okay.
or they both become null, meaning they've gone through both lists and haven't found a common node.
So there is no intersection.
Yeah.
I love how this method uses like the structure of the linked lists to help us out. We don't have to calculate lengths or anything. We're just letting those pointers do their thing.
Yeah, we're letting the pointers do the work.
It's like if that intersection's there, they're going to find it.
They're destined to meet.
Okay, so what about the complexity?
So time complexity for this is going to be O(n) plus m, because we're basically traversing each list at most twice.
Right, they might do an extra lap around the track, but that's it. What about space complexity? We're not building any giant hash tables here.
Nope. No hash tables. That's the beauty of this approach. It's constant extra space, O(1). We're just manipulating a couple pointers, so no need for any extra data structures.
So it's time efficient and super space efficient. It sounds like the two-pointer method is the winner here.
In most cases, yeah. It's generally the best approach.
Okay, so are there any situations where maybe a different method would be a better choice?
You know, there could be. Like, let's say you're in some weird situation where traversing the linked list is really expensive.
Okay.
Like, it's not common. But imagine if accessing each node takes a long time.
Okay, I see. So even though the two-pointer method takes fewer steps overall, if each step is really slow, it might not be the fastest.
Exactly.
In that case, something like the length difference approach, where we're minimizing the total number of steps, might be faster.
Right.
Okay, so let's talk about the length difference approach. How is that different from the two-pointer method?
So instead of making the pointers jump to the other list at the end, we first figure out, like, how much longer one list is than the other.
So we're doing a little prep work before the pointers even start moving.
Right. Okay.
We count the nodes in each list. Say list A has M nodes and list B has N nodes. Then we take the absolute difference, and that tells us how many extra nodes one list has.
All right, so we know which list is longer and by how much. Then what?
We use that difference to align our pointers. Let's say list A is longer than list B by deed nodes. We start a pointer at the head of list A and advance it deed steps.
So we're giving the pointer on the shorter list a head start, so they both reach the merging point at roughly the same time.
Yeah, exactly.
Okay.
Now we can move both pointers at the same time, one step at a time, and compare the nodes. If we find a matching node, that's our intersection. If we reach the end of either list without a match, there's no intersection.
This method feels like a bit of a hybrid between the brute force and the two-pointer.
Yeah, it's kind of a combination. We're still traversing the lists, but we're being a little more strategic about where our pointers start.
Right. And it's, it's easier to understand maybe, but that initial step of counting the nodes, that can be a bit of overhead.
Right. So in most cases, the two-pointer still comes out on top.
Yeah, I'd say so. But it's good to know your options, right? You can pick the best tool for the job.
This has been such a great deep dive.
It has.
We've covered brute force, hash table, the super elegant two-pointer,
Yeah.
and now this length difference approach.
4 great approaches.
And they each kind of highlight different ways of thinking about the problem, right?
Yeah, definitely. I mean, brute force is just pure power.
Yeah.
The hash table is all about speed of access.
And then the two-pointer is like a little dance of the pointers,
It is. It's a beautiful dance.
gracefully finding their way to the meeting point.
Exactly.
And then the length difference, where
Yeah.
we're just strategically lining things up before we even start comparing. It's amazing how many different ways you can approach this one problem.
Yeah. And that's what's so cool about algorithms. It's not just about finding a solution, it's about finding the most elegant one, the most efficient one.
Exactly. So even if our listeners never actually run into this specific problem in their work, the way we're thinking about it, the strategies we're using,
Right.
those are transferable skills.
Absolutely. Like the idea of pre-processing data to make things faster later on, like we saw with the length difference approach, that comes up everywhere.
That's a great point. So it's not just about linked lists, it's about broader problem solving in computer science.
Yeah, and the two-pointer technique, that comes up a lot too, not just with linked lists.
Right.
It's a good one to really understand.
It's all about manipulating those pointers.
Yeah,
This has been such an insightful deep dive into linked lists and algorithms.
I agree.
We've tackled the intersection problem, we've explored these 4 different approaches, and we've even touched on some bigger ideas in computer science.
And I think the biggest takeaway here is that understanding why an algorithm works is just as important as knowing how it works.
Yeah, that deeper understanding is what lets you take these ideas and apply them to new problems.
Exactly.
To all our listeners out there, keep experimenting, keep learning, keep pushing those coding skills further.
It's all about continuous learning, exploration. There's always a new problem to solve, a new algorithm to master, a new challenge.
Thanks for joining us on this amazing episode of AI.Code.Cast. Until next time, happy coding. So we've covered a lot of ground here. Brute force, hash table, two-pointer, even that length difference approach.
Yeah, we really went through it, huh?
We did. Is there anything else we can pull out of these solutions? Any other insights?
You know, it's interesting how each approach kind of shows a different way of thinking about the problem.
Oh, yeah.
Like brute force is all about, just raw comparison power.
Power through it.
Yeah, just tried everything. And the
Yeah.
hash table is leveraging the speed of, retrieving data quickly.
Right.
And then the two-pointer, like we were saying, it's like this elegant dance of these pointers gracefully making their way to that intersection point.
And the length difference, where we're strategically aligning things.
Yeah.
It's amazing how many different ways you can tackle the same problem.
It really is. And it shows how creative you can be with algorithms. It's not just about finding any solution. It's about finding, the most elegant one, the most efficient one.
Exactly. So even if our listeners never actually have to write code to find the intersection of 2 linked lists, the way we've been thinking about it,
Right.
the strategies, those are skills that apply to all sorts of problems.
Oh, absolutely. Like that pre-processing step in the length difference approach.
Yeah,
That's a powerful idea. And that comes up all over computer science.
that's a great point. So it's not just about linked lists, it's about bigger problem-solving ideas.
Yeah. And the two-pointer technique, that's a really good one to understand well.
Yeah, really powerful stuff.
Comes up all the time.
Well, this has been an amazing deep dive into the world of linked lists and algorithms.
It really has.
We tackled that intersection problem, we explored 4 different approaches,
Resort.
and we even touched on some big ideas in computer science.
If our listeners take away one thing from today, I hope it's this. Understanding why an algorithm works is just as important as knowing how it works.
Yeah, that's what lets you take these ideas and use them on new problems you've never seen before.
Exactly.
So all our listeners out there, keep experimenting, keep learning, and keep pushing your coding skills further.
And remember, it's a journey. Always something new to learn, new problems to solve, new challenges to overcome.
Couldn't have said it better myself. Thanks for joining us on this incredible episode of AI Codecast. Until next time, happy coding.